Hello, everyone. Welcome to the third talk in the Swiss GATT seminar. This talk will be by Corentin Bodart from University of Geneva, who will be telling us about membership problems in nilpotent groups.
Thanks. So, okay, this is this talk is going to be a bit longer than last time. So it's split like in 4 parts. So first, I'm going to introduce the 2 problems and try to give some historical motivations for them. Then we're going to focus on nilpotent groups, which is like the second part of the title. And then I'm going to tell you about 2 results. One, like more or less, I'm going to give a full proof, and then the last one only gives vague ideas. And this is based on a paper which is already on the archive. So if you want to have a look. The first problem I'm going to be interested in is the submonade membership problem. So I pick myself a group, or maybe a monoid G. And just for completeness, I'm going to fix myself a genetic set S. And then the submonade membership problem is something which is quite natural, I think. So you fix yourself key elements, some qualitative elements, which you can describe as word about the genetic set S, so some finite data. And you fix yourself an extra element G, also as a word over S. And so what you want is to find an algorithm that's, given this input, decide yes or no if the extra element belongs to the submonade generated by the key first element. So whether I can write G as a product of G1, G2, and so on. And so all I want is just to have this answer, does there exist an algorithm which has this input and always over any input it finishes, and at the end it prints either yes or no, whether this thing belongs or not. I don't want to prove, I just want the answer, and so just an answer. And then this is
one question.
Yeah.
A small question. The set G1, G2 until GK star is a group without the identity element.
So when I write star, it's the submonade generated. So it's a set of all the finite products of element from this thing, and then there's also the identity.
Okay.
Right.
Okay, thank you.
The identity is always in there, and then I have all the products of elements of G1, G2, G1, and so on. All the finite products. Okay, and sometimes when I write this, it's like a free monade. I'm going to try to make it clear when it's a submonade or when it's a free monade. And so this problem is really important historically because there is this theorem by Markov in 47. So if you take as your, in this case, a monoid G, which is the set of 6 by 6 matrices with integer entries, and you take the multiplication, then this problem actually is not solvable. So actually, even if you fix yourself G to be the 0 matrix, there exists no algorithm that, like, if you give some finite set of matrices, determine if you can write the 0 matrix as a product of those, if you're in 6 by 6 integers matrices. And so this result is really important because it's one of the first negative results, first undecidable results in all of mathematics. So some history. So what you have to think about, and so at the very beginning of the 20th century, there was the set of problem by Hilberts, and there was this famous problem, the 10 problem, which asked something which is quite similar. It's, does there exist an algorithm which, given a set of Diophantine equations, so polynomial equations with integers coefficient, and you're only looking at integer solutions, and so you're given a system of Diophantine equation, and you want to determine if the system admits a solution with integers unknowns. No, so just no algorithm. Not at all. Like even if you know exponential time, nothing. So it's really, really high up. And so this spirit of looking for algorithm, actually, it propagates to group theory and to combinatorial group theory, and in particular, Max Day in 1910, it defined 3 problems: the word problem, the conjugacy problem, and the isomorphism problem. So last week we talked about conjugacy problem. So there you're given 2 words, the 2 elements of the group, and you want to determine if they're conjugate in the group. So again, you ask for an algorithm. So there was quite a lot of hope to find algorithm for many things. And for a while, here there's the big gap. In this gap, there is a few positive results. So for instance, Dane solved the word problem in surface groups, or Magnus solved the word problem in one-related groups. But there was really no negative results, and the reason is that no one actually gave a proper definition of algorithm. And this definition only comes in 36 by Turing, which defined the Turing machine. And as soon as you give a definition, which I won't give today, he was able to give the first understandable problem, which was the arting problem, which is quite artificial in that it's like maybe self-referential, like it's a problem about algorithms, so it's a bit weird. And so the Markov result, which I just gave the slide before, is actually one of the first problems where it's understandable, but the problem is not artificial in that sense. Like it's something in semi-group theory with matrices. It really actually I only have one example which came before, which is the post-correspondent problem, which is slightly earlier. But I think this result by Markov is like the second problem, which is known to be understandable and which is not artificial in some sense. And then just to finish the story, so there are those problems. So can you solve the word problem in a group and so on? So there is a negative answer by Novik and Boone in 55. So they construct a finitely represented group where you cannot decide. There's no algorithms which, given a word, decide if it's trivial or not. And then just because it's going to be important, so the solution to the 10th problem, so with diagonal equations, there's also a negative solution in general, which was given. So it's a long proof, but it was given by Matiashevich at the end in 1970. So there's really a long story, and the result I just gave is like the first negative results, which is not quite artificial. Okay, and then the second problem I want to talk about, I need to come from somewhere else. So it comes from formal languages and from linguistics. So here I need to talk a bit about Chomsky hierarchy. So maybe you know Noam Chomsky is well known for other work. So in 56, he defined some class of languages which are more and more complex. So the goal here is to produce and recognize sentences with correct syntax. And you want to recognize them or produce them with different type of machines. Okay. So the first class, which is the only one I'm going to focus on today, is regular. It's the easier one. And this is a class of languages that you can recognize with a finite computer with the memory. It's like bounded. It doesn't depend on the size of the input. So if I have an input which is really, really long, like 10 to the 10 to the 100, the memory I'm going to need to process it and determine if it belongs or not to the language, it's still going to be the same as for a really short word. So here I gave an example. So the way we model this thing is the computer is usually a finite graph, finite oriented graph. I have some start vertex with an arrow, so you cannot miss it. And I have, in this case, I have only one accept vertex, which is going to be double, like with two circles here. And then, okay, so there are two ways to use this graph. The first way is to produce a sentence. What I'm going to do is follow a path that finishes at some accept vertex, some vertex with two circles. And then each time I cross an edge, I add a word, in this case, a word. So here, the example I gave is like, first I read a quantity. So here the idea is to recognize, produce and to recognize a legal list of ingredients you need for a recipe. So I read a quantity. So maybe I need 100 grams of flour, comma, 200 grams of chocolate, and 1 cup of milk or something. So this is the kind of, and so here I'm gonna, so what I'm checking is that the comma, there's all commas and then one n at the end. So this is what I'm checking. I'm checking for the syntax. So here, I don't want to have something else. And so reciprocally, if I want to recognize if a sentence is correct, I'm just going to read it. And each time, so I start at the start and I read it. So first I read a quantity, and so I go this way, then off, and then so you read it, and this gives you the path you have to follow. And at the end, you check if you finish. If you can always follow it and finish at an accept vertex, then you accept the sentence. I don't know if this is clear. If there's any question, don't hesitate. So this is really the simplest class of languages, and the computer we use is just a finite graph with oriented edge, which labels some start vertex and some set of accept vertices. So maybe two other examples. So first, a non-example. So if you have something, if you have someone that likes to do parentheses and has a lot of anecdotes, then if you want to parse to know if the sentence is correct, then you need to be able to see if when you only look at the parentheses, is it correctly parenthesized, right? So this is one thing you need to do to parse for more general sentences. So what you'd like to recognize is this language, the set of string of open parentheses and close parentheses, and you want it to be legal. So legal means that you never close the parenthesis which is not open yet, and at the end every parenthesis is closed, right? So a few examples is here I open, close, open, open, close, close. This is correct. Everything I've closed everything at the end, and I've never closed something before I opened it. This one is not correct though, because I open, close, close, and so I close something which is not open. Doesn't work. And this is really not legal, like it's really dangerous. You should not leave a parenthesis open, right? Because now the parenthesis is alone, it's sad. So this thing is not regular, right? Because in order to check if your word is correct, your string is correct, you need to be able to, so when you read it from left to right, you need to remember how many open parentheses there are. And if your string is really long, this is going to be some big amount of memory. So you cannot do that with a regular language. You can do it if you have a bit more memory, for example, one counter languages, but you cannot do it for regular. And then another example, which is not from language theory, but more from something you could see in computer science. So in computer science, often your input is just a string of 0 and 1. And for instance, I give a number to a computer, it can be a string of 0 and 1, and I want to know if it's a power of 2. This thing I can do with a finite computer, and the way I do it is just I just check if there is exactly 1 1. So I have a bunch of zeros with me. Then 1, 1, and then a bunch of zeros. If there's a second one, then it's not a power of 2. So this is something I can do with some finite memory. I just need to remember if I have seen 0, 1, or 2 ones so far. And I've seen 2, and I know it doesn't work. So this computer here, it can recognize if a number given binary is a power of 2. So I start with a bunch of zeros, then I see 1, I accept if I finished it there. But if I see 1 more 1, then I'm here, I'm not going to accept, right? So formal languages, it's mildly useful when you do linguistic. It's also useful in computer science. Okay. And so here the big problem is, okay, this language, so given a word, does it belong to the language or not? That's different. And this is the rational subset membership. So what I'm doing here is just pretty similar to the subdomain membership. So I define a set, which is going to be a rational subset. So it defines the finite state automatons, the finite graph I just talked about just before. And so I have my rational subset, which is defined by a finite state automaton, and then an extra element, and I want to decide if the element belongs to the set or not. And this problem is decidable for free monoids. This is really by design. This is the example I just gave. It's decidable with a machine with finite memory, because by definition, it's like this. So rational subsets of this thing, which is the free monoid, the set of all finite strings over S. This is just a rational language, and this can decide whether it belongs or not, just using the graph as I explained before. And maybe another example, it's if you take the free group, then again it's decidable. It's written by Benoit in 69. So we have two problems. One which is subdomain membership, and the other one is rational subset membership. So I'm going to give a few examples of rational subsets, which come from different kind of automata, set automata. The first example, I take this shape. So once again, I have a start vertex and a unique accept vertex. And then on each vertex, I have a loop labeled by an element in G. And in between, I have the identity. And then the rational subset, which is recognized by this automata, which is, I shouldn't really say produced by this automata, is a set of elements which I can write as a product of G1, a power of G1, then a power of G2, and a power of G3, so on up to a power of GK. The question is, given those elements, G1, G2, GK, and my extra elements, can I write it as a product of this form for N1 and up to Nk, which are positive integers, right? And actually, this special case I just defined as also a name is the taxa. It's going to come back later. Then another example. So I only have a single vertex. So it's start again, a single vertex should accept. And here I have a bunch of loops from the vertex to itself. And here the rational subset I recognize is just a submonoid generated by G1 to GK. So in particular, you see that the submonoid membership is a special case of the rational subset membership, right? So in particular, if you can solve it for the rational subset membership, then you can solve the submonoid membership. And the question is the appropriate true? So there exists a group where the submonoid membership is decidable, but the rational subset membership is not decidable. And here I'm going to give a few results. So it's no in RAGs. So I'm not going to define RAGs is. If you take a RAG, then both problems are always either both solvable or both solvable. It's also no if you have infinitely many ends. So if you're a free product, or if you're a free product amalgamated over something finite, or a national extension amalgamated over something finite, then both problems are equivalent. So one is solvable if and only if the other one is. And then maybe I should say something. So I thought this problem was unsolved, but actually it's solved. There's this example, which is if you take a Ries product of a Z2 with A, which is a finite abelian, actually, this is an example where the submenu membership is solvable, but the rational subset membership is not. So I didn't know about this example until I first gave this presentation. So this is an example. But so really the motivation here is like you have two natural problems, and you want to understand in each class of if you fix yourself to a class of group, is one more complicated than the other, and why is it? And can you find an example where it's like really more complicated because it's like one is solvable and the other one is not? So I think this is quite a natural question. Try to understand the difficulties between the difference between two problems inside different class of groups. Okay, so now I'm gonna focus on a specific class of group, which is class of nilpotent groups. So first definition. So in order to define the nilpotent groups, you need to define the lowest central series. So gamma n of G is just the subgroup you get by putting n G's and then you put the brackets correctly. So gamma 2 is the commutator subgroup, then gamma 3 is the commutator subgroup of G and the commutator subgroup, and so on. And we said that a group is S-step nilpotent. So a group is nilpotent if one of those terms is trivial, and it's more precisely S-step nilpotent if the S plus 1 terms is trivial. And an example, which is maybe my favorite, or maybe my second favorite, is the Heisenberg group. So one easy way to define it is a set of matrices with one on the diagonals, 0 below, and up here you have elements, integers. And this group is two-step for the multiplications. The way you see it is that if you take a commutator of element of this form, then you're gonna get those two on 3 to be 0. And then, so this one is the only one which is on 0, but all those elements are central. They commute with everything. So if I take one more commutator, I only get 3 elements. So this is an easy way to define it, but it's really not the way you should think about it. At least I don't think that's the way you should think about it. So when you're doing something which is more like geometric, or when you try to compute distances and so on, really the better way to think about it is through some geometrical model. Here, yes. So a geometrical model. So instead of seeing elements as matrices, I'm going to see elements as equivalent classes of paths in T squares, and they all start at 0. So I need, okay, paths in T squared, I think it's clear. What is the equivalence relation that you need? So for that, we need to define two parameters, which I'm going to associate to every path. The first one is just the endpoint. If I have some path, the first endpoint is 0, the second endpoint is something. Okay, keep that in mind. And the second parameter, which is important, is the balayage area. So you have some path, and then what you do is you close it by just a straight segment back to the identity. So now it's already closed a bit. Okay. So you close it, and then you compute the winding number of this closed path around each point of the plane. So this gives you some numbers everywhere, and you just integrate, and you get some oriented area. And then two paths are equivalent if they have the same endpoint and if they have the same area. This is one way to think about it. So here I gave an example. So I'm going to write x when I go to the right, x inverse when I go to the left, y when I'm going up, and y inverse when I'm going down. If you consider this path, I get this thing. the endpoint is 4, 4, and the area is just 8. You can try to count, because this part is positive and this part is negative. So this is a nice way to think about the algebra group. Know what you want to, you can compute the length if it's a isopermetry problem. It's really nice, I think. And more generally, if you have any two-step nilpotent groups, you can do something very similar. So here the other group I need to talk about is the free two-step nilpotent groups. So it's a generalization of the present case. So you have M generators, and then the only relation I force is that it's two-step nilpotent. So I only make sure that if I take a triple commutator as this, it's always going to be true. And this again can be seen as path and then some kind of area. So I should here's path in DM, and then okay, it's a path in the space. How do I compute areas? But actually, I have many areas I can project in any plane for two components. So I get that many projections, and in each projection I can compute the areas. So this is, and so in general, for two-step nilpotent and even for higher step nilpotent, you can always think about your group as some path in the abilization, and then you have some parameters, which is going to be either the area or maybe something higher order if you're like 3 steps or 4 steps. But you can always see them as like paths, modulus, and calculations. So this is a nice way to think about it. Okay, so those are two groups and maybe some way to think about it. And then some results with respect to the previous things. So first, there's the subgroup membership problem, which is a special case of the submodel membership. So it's when you don't only consider the semigroup generated, but the subgroup generated. So you allow yourself to have inverses. And this problem actually is already decidable from nilpotent groups. And then if you were there last week, actually the argument is quite similar. So you can look in finite quotients and then check infinite quotients. Okay. So subgroup membership, it's always decidable, but then we have all two other problems, which are more general, so the submodel membership and the rational system membership. And we also have the Knapsack problem. So the first result is for virtually abelian. For virtually abelian groups, all three problems are decidable. And actually they reduce to just something with like linear equations with linear coefficients and so on. So it's quite easy to solve. So this is in 99. And then first problem for rational subset membership. So negative result for the free two-step nilpotent group of a large rank. So here actually the proof, if you remember the Hilbert's 10 problem, it goes back to this. It's reduced to the Hilbert's 10 problem. And then you wait a bit more, and then we have a solution of a Knapsack problem, which is also negative. Also in the same group, and again it's reduced to Hilbert's 10 problem. So if you have any system, you can somehow encode it inside the N2M, and then because Hilbert's 10 problem is not decidable, this one not either. And then more recent, again negative result for the semi-group membership. So I should have written submonoid membership. So again, it's non-decidable. The only thing I'm gonna remark is that you have like 23 years in between two problems. So you can start to think that this problem is like the summary problem is simpler than rational subset membership. And so in the converse, it's easier to prove negative results in this rational subset membership than for the submodel membership. And then there's this last column. So the first result was for the Knapsack problem. It's always solvable, and again it goes back to Diophantine equation. So here it's a special case. So I said in general, it's not decidable if a Diophantine equation admits solution. If you have a single Diophantine equation which is quadratic, in however many variables, you can always solve, like decide whether or not admit solutions. And this is what's used for this problem. And then the last result is this result, which is more recent, but actually surprisingly, it's really elementary. It's again just some linear program. So this problem, this result, it relies on really deep results in quadratic Diophantine equation. This one is elementary. This one is elementary. This one, and those are all really complicated. So this maybe hints to the fact that again, semi-group membership is easier than rational subset membership. So here, okay. And all problems were open for rational subset membership. Okay, maybe one less at the end of this. Okay, so what I'm going to try. Yeah, question.
So just how do you define the H map here?
Right. Okay. So this thing.
Yeah.
So okay, when you're H is the Hirsch length. So it's defined for all nilpotent groups. So in particular, it's defined for the commutative subgroup of nilpotent groups. It's also defined for polycyclic group. Anyway, so this is, but in this case, all my groups are two-state nilpotent. So what I know is that this thing is central to its abelian. So it's going to be isomorphic to something like this, right? Because it's abelian. And this H is here. This H is the H length in two-state nilpotent. So my derived subgroup is going to be abelian. I have some torsion maybe, and then I have some free abelian parts. And the rank of this is my H length. And actually, this the reason I put this column here is that it tells you how many polynomial equations you can store, quadratic polynomial equations you can store in the group. And so you see when you can store a lot of them, then you can encode the negative solution to the Hilbert problem. When you only have one of them, then you can solve it. Right? This may be the reason why it's hard for certain and easy for others.
Okay.
This is just okay.
Yeah, okay. Thank you. And the H2M plus 1, this group said, is the
right
nilpotent nilpotent group with the
right. So this is the free two-state nilpotent group, which I defined earlier.
Yeah.
So it's rank M, so it's generated by M elements. So the abelian is going to be rank M. And then the derived subgroup is rank M choose 2 is the number of areas here. So you can project to any pair of coordinates, you get an area. This is basically the parameters you're tracking with this part for this group.
Okay. Thank you.
Okay. Okay, we're going over time. So first, dimension reduction. So I'm trying to. This proof is motivated by the proof for the submodel membership for the Heisenberg group. So here I have this result. So there is this algorithm which takes as input finitely represented nilpotent groups. So I take the group as a finite representation, a finite set, and an extra element G. So all the data I need for the submodel membership. And then its outputs finitely many instances of the rational subset membership. But what's interesting is that it's instances inside some subgroup H of G. And if the subgroup has the same the derived subgroup has the same Hirsch length, and actually I can solve it. So if I just have all those indices and I solve each of them, and then if any of those return positive, then I know that G belongs to my submonoid and otherwise doesn't. So what I'm doing here is I'm reducing the submonoid membership in a group to some rational subset membership in a smaller group. So here's the proof. It's 2 slides, maybe 3. It's more like complete. So what you do is you first consider the torsion-free abelianization of your group. So I abelianize, then I get something with torsion. I kill the torsion too. So I have my map from G to some Z to the R. And then I consider the convex hull of my set S. And I'll also look at the minimal phase of this convex hull, which supports 0. Then I need to define 3 things. The first thing is the subgroup in which I'm going to solve my membership problem, my rational membership problem, is the inverse image of the vector space generated by the phase, which supports 0. This is a subgroup of G. And I'm going to define 2 subsets of S. So the first one is just the intersection of S with H, and the other one is the rest. So the way you should think about this is elements in S0. So elements in S0, maybe this thing's better. Elements in S0, those are basically those 2 things. Maybe I have some other on the edge. When I use element in S0 and I look in the abelianization, I do something which I can undo because I can come back. So this is for S0. For S0, I do something in abelianization, I can undo it. For S plus, for instance, if I use this one, well, each time I use this one in a product, I'm going to get higher and higher. But because it's not in the phase which on its 0 lies, there's nothing. So if I use this one, there's nothing below. And so I'm just going to get higher and higher and not being able to come back down. So those are the elements where I can do and undo in the abelianization, and those are the ones where I cannot undo it in the abelianization. So I separate it on those 2 things. Now if I fix myself an element G, then there's something which is really nice, is that there's only finitely many words over S plus, which are gonna evaluate at the same thing as G modulo the vector space F. So if my G is somewhere here, sorry. If I use too many times elements here, I'm going to shoot past G, and so I cannot be the same coset as G. Right. So each time I use those, I'm going to get further and further in one direction, and eventually I'm going to shoot past G modulo the vector, this vector space. So if I only look at the letters from S plus, I only have finitely many possibilities that are possibly lend me to something which is equal to G. And so what I need to check is for all those words which satisfy this thing, does G belong to this set? So if no, I forgot for the letter from S0 for a while. If I put them back in, can G be something in there? And I can rewrite it as this shape. So just doing some conjugation, I can rewrite it just as a product of some submonoid and then some other submonoid, then some other submonoid. And all those things here, they belong to H. And also this thing belongs to H. This is an instance of the rational subset membership in H. So now if the H length is smaller, I'm happy because an instance of the rational subset membership is something which is smaller. So I'm happy. So what happens if the two H lengths are equal? Then maybe I have not done any progress. Maybe H is just G, so I have not done any progress. I mean, I end up with something which is a harder problem. So yeah. But in this case, there's a small miracle. So if I have a finitely generated nilpotent group and some subsets inside it, then again I can consider the torsion-free hybridization. And then there's two things that are equivalent. The first one is zero lie in the interior of the convex hull of the image. What this means is that when I project, I get something which is full dimensional, and S0 is something in the middle. And this is equivalent to the fact that the submonoids are generated by S0. It's not only a submonoid, it's a subgroup, and better than that is a finite index. Okay. So this is really nice. And why is it nice? Because if I have this condition, then this means that the torsion-free hybridization of my subgroup actually is just a restriction of the torsion-free hybridization of G restricted to H. So everything that died when I hybridize G, so every commutator in G, it's also a commutator in H. So this is the thing. So everything that doesn't die. So it's just a restriction, and so in particular the convex hull of S0, but well, S0 is the set of points that lands in the subspace. So it just, I mean, okay. Let's just go back to the image. S0 is all the points that are products here. In particular, I have those two because otherwise it's going to be a face. And so F actually it's equal to the convex hull of tau of S0, but because F was the minimal phase, we can conclude that actually 0 belongs in the interior of the sphere. So we can apply the theorem, and then now this question, because this thing is a finite index subgroup, I can do everything modulo this thing. So I reduce myself to some problem in something finite, which is quite nice. And because everything is something finite, I can just solve it. So this is the end of proof. And the corollary is that there exists a group where the submonoid membership is decidable, but the rational subset membership is not decidable. And the example is the following. You take a group of this form. So by a result I said earlier, we know that there is some group of this form for which the rational subset membership is not decidable. And what I'm just going to do is take such an example with M, which is minimum. And now I'm proving that actually this group, the submonoid membership, it is decidable. So the reason is that for any subgroup of G, so when I apply the previous result, I'm going to reduce myself to rational subset membership in some subgroup H of G. If this thing is equal, if those two things are equal, then I can solve it, so I don't need to care about it. And so the only case I care about is when this H length is pretty smaller than the H length for G. But then we have this caracterization of all the subgroup of G of this form. They're all of the same form, with K which is smaller than M, and this thing which is smaller than something. But if we have this thing, then this implies that K actually is strictly smaller than M. And then by minimality of M, we can conclude that the rational subset membership is decidable in all those subgroup H, and so we can solve the problem. So this is the thing. And okay, I don't have much time, so I think I'm gonna go faster, and skip some part. So other results, which is in the paper, is that the rational subset membership actually is decidable in the Heisenberg group, which I defined earlier. And so one corollary of this is that the submonoid membership is decidable inside some other group, which is the Philippon three-step nilpotent group. This is just a nice corollary. So this group is just each length is 4, and every subgroup is either virtual abelian or Heisenberg. Either any proper subgroup is either virtual abelian or Heisenberg. And so because we have this extra result here, we can solve the Simon membership. And then there's this night conductor which I'd like to solve. But if anyone is interested, I'd be happy to see it solved too. If you can solve the same problem in all those groups, so something a bit more general, then actually, so first it's nice on its own, but also it proves the subdomain membership for many groups. So that'd be nice. So here I thought I would give some ideas, but I think I'm going to stop here because it's messy anyway. So okay, I'll stop here and skip to the thanks.
Okay, let's thank Corentin. Are there any questions for the speaker?
Yeah, I have a question. Hey, super interesting stuff you're doing. I was curious about the way you see Heisenberg groups. And so this Bailage area that you mentioned looks conceptually similar to what in the real case I would probably call path signature.
Mm-hmm.
So my question is, have you seen path signatures? And if yes, do you know if there's kind of a direct link to the two-step nilpotent groups?
So I don't know exactly what path signature is, but there's definitely a continuous case of this thing. So I don't know if you can. So yeah, so actually, it's come from. So the motivation is definitely continuous. So where is it? So yeah, you can. I mean, okay. So yeah, I just don't know what path signature, but you can do the same thing in R square, and then you have the same lift, and this is, if you know all the subremanent thing or subfincher, this is really the same. But,
okay,
yeah.
and are there specific groups that are known, or like if you do this in the real case, is this still kind of a topic in group theory, or do we get out of the realm of group theory and enter something else?
So so this is also something I do in the real case, not for a decision problem like this, but for more like geometric reasons. So I don't know if it's still in geometric group theory, but it's definitely what I'm doing.
Mm-hmm.
But yeah, maybe then you should go more. You go borderline to geometric analysis. And yeah, there's. I mean, all the keyword are those. So subfincher geometry, all those things. So it's definitely something which is interesting. The key interaction with group theory is that it's distributed by Consu that allows us to compute the gross groups using the continuous version.
Sorry, what is this?
Maybe the keyword is the name of someone. If you're interested, you should go to Fribourg and talk to him.
Yeah, I guess I'll check him out. Can you just tell me what is this word? Subfine geometry.
Finchler.
Fin.
So Finchler is a. So okay, you probably know Riemannian.
I heard of him, yeah.
Finchler is what happens when your ball is no longer a ball, but some is it better? Written.
Sorry?
So when the ball is like some polytope or something, so just something convex, but something smooth or something like coming from a periodic form.
Okay.
And then you add the sub. Okay, that's something different. Like you need distribution, and it's fine.
Cool. Thanks.
Yeah, if you have a precise question, I'd be. Or if you want to talk about that, I really like this subject. So. But
Cool.
yeah.
I'll check out your keywords and then maybe I'll come back to you.
Do you know ways to characterize performance passes?
So characterize a column class. In which case?
For let's say
For any two-step buttons? Yeah, for any two-step button, you get something similar. Because any two-step button is a central extension of the abelianization. So it's indeed just pass in deabelianization. And then, I mean, it's going to be some quotient of the free ones. So you're going to get something like you have some area, but maybe you only care about the parity of the area, or you care about the sum of the areas, or maybe you don't care about some areas. There's always some model like this. But then finding the correct one for your group.
Yeah, I guess there are infinitely many options for natural response.
So is there an infinite class in one? Yes. Yeah, always. Yeah. Actually, yeah. But then what's interesting is like finding short ones. That's really fun. Anyway.
Sure, this one would be unique or?
No, sometimes it's close to unique.
Yeah, it's a binomial.
Right, so there's some case where it's just binomials. No, because there's areas, so you get some partitions. You get some fun stuff for you. So yeah.
If you shrink this out to the equivalent, counting the equivalence passes.
Right, so I think the number of geodesics from here to here, where the area for this thing, is going to be the number of partitions. We have the same area here, and we're the two endpoints, actually the same maximal side of the part and the same number of parts. Okay, probably it's messed up because you can have zeros. So you're gonna get something similar on partition. Okay. Question from online.
Are there any more questions for the speaker? I'll give it a few minutes. Sometimes people are.
Just one question. There is something known for the solvable words like Pomslock Solitaire in the blackboard. In the blackboard in the board that you talk about.
Here.
Yeah.
Yes.
Okay.
So for Pomslock Solitaire, yes. This is solvable, and so all of them are solvable.
Oh, okay.
But so in solvable, there's this other example I gave, was this one. So for the first one, so if you take A, which is finite abelian, finite, then all of them are solvable, and this one is solvable. This one is solvable. This one is not. But then, yeah, there's really interesting stuff if you go further. So this one is not, this one is. If you take this is an open question if you want to try. And yeah, there's plenty. I don't know what's your favorite solvable group. But yeah, probably there's interesting stuff. If you take like something like this, where Z is acting hyperbolically to get solved, I don't know what you get. Maybe you get something interesting.
Okay. Okay. And do you know for a red product with the ZN, the other one, or just until 3 for the moment?
Right. So it goes to so if it's solvable for subgroups. So in particular, we have So here it's always no. Wait, no, not this. If you go down, it's always no, and then down is no.
Ah, okay.
And
Okay.
here it's always yes.
Yes,
For
yes.
other reasons.
So,
Actually, is it no? No, okay, this is not no. This is. Okay, this is no, I think. So the reason here is that it's the word problem is context free, and then the nicer problem. So I don't think it's not for those two. Anyway, much fun. Like infinite amount of work if you want.
thank you.
Are there any more questions?
And yeah, I have a still one question. How do you use the automaton to compute the things like U inverse inside of the automaton? I mean, because I guess it's in some
Wait. Oh yes. Why is this a special case of the? Why is this a special case? That's the question.
yes.
Tendencies of the.
Yes, how do you use the automaton to compute it?
So the automaton for this one is going to be something like this shape. So okay, I have start. Then I have here I have all the elements of S0. So I have say S0 is ABC, I don't know. Then I get and then okay, then I have some other thing, and here I have U1A, U1 inverse, U1B, U1 inverse, U1C, U1 inverse. Okay, this is not readable. Yeah, nothing here. So it's just going to be like this. So I have a bunch of cells, and on each cell I put something so that I get this submonade. And then here I'm going to put the submonade, but the generators is going to be conjugates. So, does this make sense? So in the end, the shape is going to be something like this. And then on each of them, I have like. This is like a special, like not the worst case of a rational subset.
Okay.
It's pretty representative of what you can get.
Thank you.
Okay, are there any more questions? Bruno, any more? Or anyone else? Any more questions? I'll give it a minute. Sometimes people are a bit shy.
Sometimes
Okay.
you need to stop recording to get the questions.
Yeah, okay. It seems like no more questions. So for the moment, so let's thank the speaker one more time.